A red-black tree becomes super easy once you know this idea. We're talking about left-leaning red-black tree in this video specifically, and the idea is that a red-black tree is basically a binary representation of a 2-3 tree, meaning that for every 2-3 tree, there is a 1-to-1 mapping of a 2-3 tree to a red-black tree. And let's just see how it goes. The left leaning in this case means that a red node is always leaning to the left of a black node. What does this mean? We'll soon know what this means. Well, before that, if you don't know what a 2-3 tree is, I have made a video about it already. You could check it down in the link description if you haven't know what it is. But and the reason that we say it is super easy once you know what a 2-3 tree is, what a red-black tree is if you know what a 2-3 tree is because you could always do insertion, deletion, and all those kind of operation in a 2-3 tree when being asked what a red-black tree representation of a series of insertion or deletion will become. You could draw a 2-3 tree in the first place, and then you just map it to a red-black tree directly, and it's just that simple. Well, yeah, let's look at an example. The mapping is something like this. We know there is only a 1-key node or a 2-key node allowed in a 2-3 tree. And so for a 1-key node, we could simply map it to a black node in a left-leaning red-black tree, and a 2-key node can be mapped to a black tree following by a red link to a red node in a left-leaning red-black tree. Yeah, let's do an example. So this is a vetted tree in a 2-3 tree. We transform it like what we said in this mapping. Well, first of all, let's draw the 5. This is normal. And in this case, we have a 2-key node. What we do is that, so we've mentioned that a 2-key node will be represented in a left-leaning red-black tree like this. And in order for this to still be searchable, we could see, of course, we're going to have the value that is bigger on this side and a value that is smaller on this side. And this is what we do. We connected this part, and you see we have 8 here, and of course the 6 will go to the left. And yeah, this is the representation of mapping a 2-3 tree to a red-black tree in this case. Another example, the same thing applies. For the 2-key node, we have the larger value right here, and we transform to something like this. This is how you map the 2-key node to a red-black tree representation, like so. And we connect the rest just like how we do. And for every other stuff, of course, it's going to be connected just like so. And this is example 2. And of course, we might have this tree in 2-3 tree. It is as simple as it is. We're connecting it like so. And yeah. And here's some great fact about red-black tree that could be easily understand once you know where it comes from and how you map the node from 233 to a red-black tree. Number one, it is a self-balancing tree. Of course, because from the fact that it is a binary representation of a 2-3 tree, we know a 2-3 tree is self-balancing, and so whatever it is, well, it is balanced already, and we are only transforming into a binary representation. Of course, it is still self-balancing. And number two, the root is always black. Of course, because either you have a 1 key node as a root or a 2 key node as a root, the root after the transformation will always have the black node on the top. And so the root is always black. That is correct. And number three, the same amount of black nodes or black links on any path from root to leaf is the same. And that is also true, because by observing we could see that a 2-3 tree links to the black, well, yeah, a 2-3 tree's link is a black link in a red-black tree. And so, and because that a 2-3 tree has all the leaves at the same level, of course we're going to have the same amount of black links from any path from root to leaf. Yeah, thank you.